तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. This is the third lecture of Module 5 on Analysis and Design for Shear and Torsion. In this lecture, we shall study the design for shear. First, we shall study some general comments. Next, we shall move on to the design steps, and then we shall study the design of stirrups for flange. First, general comments. The objective of design is to provide ultimate resistance for shear, which we shall denote as VUR, greater than the selected shear demand under the ultimate loads, which we shall denote as VU. Thus, first we need to know the shear demand VU. For simply supported prestressed beams, the maximum shear near the support is given by the beam theory. For continuous prestressed beams, a rigorous analysis can be done by the moment distribution method, or else the shear coefficients of table 13 of IS 456-2000 can be used under the conditions of uniform cross section of the beams, uniform loads, and similar lengths of span. Thus, at the beginning, we have to do an structural analysis to get the design ultimate shear. If you are having a simply supported beam, then the shear can be calculated by the conventional beam theory. For a continuous beam, we can do a rigorous analysis, or else the coefficients that are given in IS 456-2000 can be used, provided we satisfy the limitations of uniform cross section, relatively equal span, and uniform loads in the different spans. The design is done for the critical section. The critical section is defined in clause 22.6.2 of IS 456-2000. In general cases, the face of the support is considered as the critical section. Once we traverse from the middle of the beam towards the support, for a uniformly distributed load, the shear increases. Now, the shear at the face of the support can be used for the design, because once we enter the support, then the depth of the section is large and we do not expect a shear failure. When the reaction at the support introduces compression at the end of the beam, the critical section can be selected at a distance effective depth from the face of the support. In special situations like, say, a simply supported beam, when the reaction generates a state of compression in the concrete over the support, then the code allows us that we may consider the critical section to be at a distance of effective depth from the face of the support. The reason is, when the concrete is under compression, the strength of concrete to resist shear increases. A simple way to consider the increase in the shear capacity of concrete is to design for a section which is at a distance effective depth from the face of the support. The effective depth is selected as the greater of dP or ds, where dP is the depth of CGS from the extreme compression fiber and ds is the depth of centroid of non-prestressed steel. Since the CGS is at a higher location near the support, the effective depth will be equal to ds. We have two depths for the two types of steel. One is for the prestressing steel and another is for the non-prestressed steel. Usually at the supports, the depth of the non-prestressed steel is larger than the depth of the prestressing steel, and hence the effective depth can be considered as the depth of the non-prestressed steel. To vary the spacing of stirrups along the span, other sections may be selected for design. Usually, the following scheme is selected for beams under uniform load: close spacing for quarter of the span adjacent to the supports, wide spacing for half of the span at the middle. For large beams, more variation of spacing may be selected. Let us understand this from the following sketch. Since under a distributed load, the shear varies along the length of the span, we may vary the spacing of stirrups to economize the amount of steel used for stirrups. For a beam with uniformly distributed load, the convention is that to provide a close spacing of stirrups in the two ends of the beam, the length of the two ends is about the quarter of the span, and for the middle, the spacing of the stirrups is wider than the spacing at the two ends. In this sketch, the two ends have closer spacing of stirrups, the left end and the right end, whereas the middle half of the beam has wider spacing of stirrups. Of course, the spacing should satisfy the maximum spacing requirement. When we design the stirrups in this fashion, we have two design sections, one at a distance d from the face of the support and another at a distance L/4 from the center line of the beam, where L is the span of the beam. For the design of stirrups, the following quantities are known. First, Vu, which is the factored shear at ultimate loads. This is calculated from VDL and VLL. VDL is the shear due to live load and VDL is the shear due to dead load and VLL is the shear due to live load. After a member is designed for flexure, the self-weight is known. It is included as dead load. Thus, for gravity load design, the shear is known from the dead load and the live load. The self-weight of the beam, which is known after the section has been designed for flexure, is included as dead load. Once we know the shear due to dead load and live load, we can calculate the ultimate shear due to the factored loads by placing the suitable load factors. If we have other types of loads like lateral loads, then we have to calculate Vu as per the load combinations specified in IS 456-2000. The grade of concrete is known from flexure design. The grade of steel for stirrups is selected before the design for shear. As per IS 1343-1980, the grade of steel is limited to Fe415. Thus, before we embark into the shear design, we know the material properties. The grade of concrete has already been finalized from the design for flexure, and the grade of steel is selected before the shear design. The grade of steel is limited to Fe415. It should be Fe415 or a lower grade, such that there is adequate ductility in the stirrups, and with this we start to calculate the unknown quantities. The following quantities are unknown: Vc, which is the shear carried by concrete; ASV, which is the total area of the legs of stirrups within a distance SV, and SV is the spacing of the stirrups. Next, we are moving on to understand the design steps for the shear design of a member. The steps for designing stirrups along the length of a beam are given below. First, calculate Vu at the critical location. This can be calculated from the analysis or by using coefficients given in IS 456. Second, check Vu divided by B dt to be less than tau c max. The value of tau c max is given in table 7 IS 1343-1980. If it is not satisfied, increase the depth of the section. Here B is the breadth of the web, which we earlier had denoted as Bw, and dt is larger of dp and ds, which are the two depths for the prestressing steel and the non-prestressed steel respectively. As I had mentioned earlier, that the design for shear involves not only the design of stirrups, but making sure that the different modes of shear failure are restricted. The purpose of checking the maximum shear stress to be within a certain value is to ensure that the concrete does not crush under the shear compression failure, and hence we need to make sure that the average shear stress at the critical location, which is given as Vu divided by B dt, is less than the maximum permissible shear stress, which is tau c max given in the code. The tau c max is given for different grades of concrete. If we plot the values, then we observe that there is an increase of tau c max from grade 30 to grade 60, but roughly the value of tau c max is around 4 Newton per millimeter square. The third step is to calculate Vc from the lower of Vc0 and Vcr. In my previous lecture, we studied that there are two expressions of the capacity of concrete to resist shear. One is for an uncracked section, which is denoted as Vc0, and another is for a cracked section, which is denoted as Vcr. Usually near the supports, Vc0 will govern the value of Vc, whereas near the middle of the span, Vcr will govern the value of Vc. Whichever is lower out of Vc0 and Vcr, that we are selecting as Vc. Vc0 is given as 0.67 times B times the total depth d times root over ft square plus 0.8 fcp times ft, where d is the total depth, ft is the direct tensile strength of concrete, fcp is the prestress at the level of the CGC, and we have a 0.8 times the pre-stress to be on the conservative side. The VC0 has two terms. The first term on the left represents the shear required to change a flexural crack to a flexure shear crack. It is dependent on the value of tau c and the amount of pre-stressing force. And the second term is the shear that corresponds to the moment causing a flexural crack at that critical location. The value of VCR need not be less than 0.1 BD root over FCK. In presence of inclined tendons or vertical pre-stress, the vertical component of the pre-stressing force, which is denoted as Vp, can be added to Vc0. Thus, the code allows us to take advantage of the curved profile of a tendon in a post-tension beam, because the vertical component of the pre-stressing force adds up to the shear resistance, and it can be added to the contribution from concrete. The code says that Vp can be added to Vc0, which is the expression for an uncracked concrete, but Vp cannot be added to VCR, which is the expression for a cracked concrete, because after cracking the effect of pre-stressing is not significant. The fourth step is to calculate ASV by SV, where ASV is the area of the stirrups and SV is the spacing. If VU is less than VC but greater than VC by 2, thus the demand is less than the capacity of the concrete, but it is greater than half the capacity of concrete, then minimum amount of stirrups needs to be provided. The minimum amount of stirrups is given by the following equation, which is ASV divided by BSV is equal to 0.4 divided by 0.87 Fy. This equation is based on the concept that the stirrups have to have a stress of minimum of 0.4 Newton per millimeter square. This is the expression to calculate the minimum amount of stirrups and the spacing, which is given as the ratio ASV divided by SV. Another provision for minimum amount of stirrups, which we shall denote as ASV min, is as follows. In presence of dynamic loads, ASV min is equal to 0.3% of AWH is equal to 0.2% of AWH when the total height h is less than or equal to 4 times BW. With high strength bars, ASV minimum is equal to 0.2% of AWH is equal to 0.15% of AWH when h is less than or equal to 4 times BW. In absence of dynamic load, when h is greater than 4 times BW, ASV mean is equal to 0.1% of AWH. There is no specification for ASV mean when h is less than or equal to 4 times BW. Thus, there is a second requirement of minimum amount of stirrups, and this requirement is based on the horizontal area of the web. The expression of the minimum amount of stirrups is given as a certain percentage of the area of the web for a horizontal section. If VU is greater than VC, that means the shear demand exceeds the capacity of the shear resisted by the concrete. The amount of stirrups is based on the following equation. ASV divided by SV is equal to VU minus VC, which is the shear to be carried by the stirrups, divided by 0.87 Fy divided by dt. Thus, This expression is used to calculate the amount of stirrups when the shear demand exceeds the shear capacity of the concrete. And this expression is based on the truss analogy for the study of shear. The fifth step is to calculate maximum spacing and round it off to a multiple of 10 millimeters. The maximum spacing is 0.75 dt or 4 times Bw, whichever is smaller. When Vu is larger than 1.8 Vc, the maximum spacing is 0.5 dt. The purpose of having a maximum spacing is that a diagonal crack should be intercepted by at least one stirrup. Hence, the spacing is restricted to 75% of the effective depth, which is represented as dt, or 4 times Bw, whichever is smaller. If the shear demand is high, that means if Vu is greater than 1.8 times Vc, then the maximum spacing is restricted to 50% of dt. Sixth is calculate the size and number of legs of the stirrups based on the amount required. And we have to do the proper detailing of the stirrups. We have to provide standard hooks at the ends. We have to make sure that there are longitudinal bars at their bends, and that will finalize the shear design at that particular critical location. Repeat the calculations for other locations of the beam if the spacing of stirrups needs to be varied. As we had mentioned earlier, that to economize the amount of stirrups, we may vary the spacing along the length of the beam, and in such a situation we may need to repeat the calculations from the design steps from 1 to 6 for the other locations that we are selecting. It is left up to the designer to select the number of variations of stirrups in a beam. A simple convention has been suggested here to have a close spacing at the two ends and a wide spacing at the central half. There is another consideration, which is the design of stirrups for flanges. For flange section, although the web carries the vertical shear stress, there is shear stress in the flanges due to the effect of shear lag. Horizontal reinforcement in the form of single leg or closed stirrups are provided in the flanges. The effect of shear lag can be explained based on theory of elasticity. When a beam bends, the total flange does not bend equally throughout the width of the flange. There is a shear lag effect, that means parts of the flange which is closer to the web, they have higher stress, whereas the parts away from the web have lower flexural normal stress. This variation of normal stress in the flange generates a shear stress, in plane shear stress within the flange, which is called the shear lag effect. Stirrups need to be provided in the flanges for the shear lag effect. In conventional reinforced concrete design, the transverse reinforcement in the slabs is adequate enough to be the shear stirrups for the shear lag effect. But for prestressed concrete beams, when the beams are precast, in that situation we need to provide separate stirrups in the flanges to take care of the shear lag effect. The sketches below show the following quantities in an I section with flanges of constant widths based on elastic analysis. We shall see the shear flow diagram. Shear flow means it is the product of the shear stress times the width of the flange or the web. We shall see the variation of shear stress in the flange, which will be represented as tau f. We shall see the shear force in the flanges, which will be represented as Vf, and we shall calculate the ultimate vertical shear force, which is represented as Vu. In this sketch, in the left hand side, we see the shear flow diagram in an I section with constant width of the web and constant depth of the flange. The shear flow increases from the end and it becomes maximum at the center of the flange. Correspondingly, the shear stress, which is the shear flow divided by the width of the flange, increases from 0 to a maximum value at the center of the flange, and on the other side of the flange the variation is similar, but the sign is in the opposite direction. This is the variation of the shear stress in the flange of a beam. Then the shear flow goes down vertically and then it spreads out in the bottom flange in the same way as we have seen in the top flange. The shear force can be calculated by the area of the shear stress diagram. Vf is the shear force acting in the flange, Vu is the vertical shear which is acting in the section, and we shall calculate Vf from the variation of the shear stress in the flange. Bf is the breadth of the flange, Df is the depth of the flange. The design shear force in a flange is given as follows: Vf is equal to half of tau f max times the area, which is half of Bf times Df. This expression is obtained from the linear variation of tau f. If we calculate the area of the stress diagram, we calculate the shear force in the flange, which is half times the maximum shear stress times the area of half of the flange, which is equal to half of the breadth of the flange times the depth of the flange. Here, to repeat, Bf is the breadth of the flange, Df is the depth of the flange, tau f max is the maximum shear stress in the flange. Thus, we have an expression of the shear force that acts in the flange. Next, we have the expression of the shear stress. The maximum shear stress in the flange is given as follows: tau f max is equal to Vu, which is the vertical shear force acting in the section, times A1 times y bar divided by I divided by Df. Here Vu is the ultimate vertical shear force, I is the moment of inertia of the section, A1 is area of half of the flange, y bar is the distance of centroid of half of the flange from the neutral axis at CGC. The expression of tau f max can be derived based on the elastic analysis. It is analogous to the expression of a shear stress at a level of the web, and it is expressed in the terms of the area of half of the flange and the distance of the centroid of that area from the CGC. Once we calculate these quantities, we can calculate tau f max from Vu, and from tau f max we can calculate Vf, and we can design the stirrups in the flange for Vf. The amount of horizontal reinforcement in the flange, which we shall denote as ASVF, is calculated from VF as follows. ASVF is equal to VF divided by 0.87 Fy. Thus, the design equation is similar, that VF is the shear force which is expected to be carried by the stirrups. Here we are not considering any contribution of the concrete, and given the maximum permissible stress in the stirrups, we are able to find out the amount of stirrups that is needed in the flanges. The yield stress of the reinforcement is denoted as Fy. Next, let us understand this design of stirrups through the help of an example. Design the stirrups for the type 1 prestressed beam with the following section. The location of tendons is shown at the midspan of the beam. This is a symmetric I section. The breadth of the flange is 435 millimeters. The depth is 100 millimeters. The width of the flange web is 100 millimeters. The prestressing is done by 10 number of 7 wear strands with an effective pre-stress of 826 kilonewtons, and they are provided in 2 ducts with CGS located at 290 millimeters below CGC. This is the section we had designed under the design of type 1 section. Longitudinal reinforcement of 12 millimeter diameter is provided to hold the stirrups. The properties of the sections are as follows. Area is given as 159,000 millimeter square. The moment of inertia I is equal to 1.7808 times 10 to the power 10 millimeter to the power 4. The area of the prestressing steel is 960 millimeter square. The grade of concrete is M35, and the characteristic strength of the prestressing steel FPK is 1470 Newton per millimeter square. The effective prestress FPE is 860 Newton per millimeter square. The uniformly distributed load, including the self weight, is WT is equal to 30.2 kilonewton per meter. The span of the beam L is 10.7 meters. The width of the bearings is 400 millimeters. The clear cover to longitudinal reinforcement is 30 millimeters. Thus, the variables after the flexure design of the beam are given, and now we are designing the stirrups for this beam. The first step is to calculate the shear demand Vu at the critical section. Here, neglecting the effect of compression in concrete, we are calculating Vu at the face of the support. The expression of Vu is equal to 1.5 times, which is the load factor, times Wt within bracket L by 2 minus x, where x is the distance of the face of the support from the center line of the support. Since the supports are 400 millimeter wide, the value of x is half of 400 millimeters, which is 200 millimeters, equal to 0.2 meters. Once we substitute the values of Wt, L and x in the expression, we get the value of the shear demand at the critical section. Vu is equal to 1.5 times 30.2 times within bracket 10.7 divided by 2 minus 0.2, which is equal to 233.3 kilonewton. Here x denotes half of the width of the bearing. Thus, the shear demand for this beam is 233.3 kilonewtons at the critical section. Next, we are checking the average shear stress to be within the maximum permissible value. To do that, we need to calculate the effective depth dt, which will be governed by the depth of the non-prestressed steel, and we are estimating that depth equal to the total depth minus cover minus diameter of the stirrups minus half diameter of longitudinal bar. The diameter of the longitudinal bar is given as 12 millimeters. We are assuming the diameter of stirrups to be 8 millimeters. Thus, dt is equal to the total depth 920 minus the cover, which is 30, minus the diameter of the stirrups, which is 8, minus half of the diameter of the longitudinal bar, which is 12, and it gives the effective depth equal to 876 millimeters. The average shear stress at the critical section, here we are substituting Bw for B, that means Bw, which is equal to 100 for the web, is substituted in that expression. Thus, Vu divided by Bw dt is equal to 233.3 times 10 to the power 3 to convert kilonewtons to Newton, divided by 100 millimeters times 876 millimeters, which gives the average shear stress to be 2.7 Newton per millimeter square. Tau C max for M35 is 3.7 Newton per millimeter square, which is available from the table or the graph that we had seen before, and we said that the maximum permissible shear stress is around 4 Newton per millimeter square, and here we find that the average shear stress is less than that 3.7 Newton per millimeter square, hence the depth of the section is adequate. Third, calculate Vc from the lower of Vc0 and Vcr. Vc0 is given by this expression. First, we need to estimate the cracking stress Ft. Ft is given as 0.24 root over Fck, which is 35, equal to 1.42 Newton per millimeter square. This is the direct tensile strength of concrete. The other term that we are estimating is Fcp, which is the compressive stress in concrete at the level of the CGC, and we are just taking the numeric value of Fcp is equal to Pe divided by A. Pe is 826 times 10 to the power 3 newtons divided by 159,000 millimeter square, which gives a compressive stress of 5.19 Newton per millimeter square at the level of CGC. Substituting the values, B is equal to the width of the web, which is 100, D is the total depth 920, Ft is 1.42, Fcp is 5.19, and substituting the values we get Vc0 is equal to 173.4 kilonewtons. We can add the vertical component of the prestressing force to Vc0. Since this is a post-tension beam with a parabolic tendon, we are taking advantage of the vertical component of the prestressing force. The vertical component of the prestressing force can be found out from the equation of the parabolic tendon. Y is equal to 4 times Ym divided by L square times x times within bracket L minus x. This is the equation of the parabolic profile, where Ym is the vertical displacement of the CGS from the ends. The following is the expression of the slope of the parabolic tendon at a point. The slope is given as tangent of theta equal to dy by dx is equal to 4 Ym divided by L square times L minus 2x. Thus, to know the vertical component of the prestressing force, we have to find out the slope of the parabolic profile. At x is equal to 0.2 meters, which is our section for design, y is equal to 20 millimeters. this we have found out from the equation of the parabola. Dy dx is equal to 0.105, from which we can calculate theta equal to 6 degrees. The vertical component of the prestressing force Vp is equal to Pe times sin theta, and Pe we know as 826 kilonewtons, and sine of 6 degrees is 0.104, which gives the vertical component of the prestressing force as 86 kilonewtons. Vc0 plus Vp is equal to 173.4 plus 86 is equal to 259.4 kilonewtons. Thus, we have found the first expression of Vc, the capacity of concrete, which is equal to 259.4 kilonewtons. Second, we are calculating the expression of Vcr, which is equal to the term which gives the shear to change a flexural crack to a flexure shear crack, plus the shear which corresponds to the generation of a flexural crack. In this expression, we are first calculating FPE by FPK, the ratio of the effective pre-stress divided by the characteristic strength of the steel, which is equal to 860 divided by 1470 equal to 0.58. Next, to calculate tau c, we need to know the percentage of prestressing steel provided. The percentage of prestressing steel is given as 100 times AP divided by BD, where D is the depth of the CGS at the critical location. D is calculated as the depth of the CGC, which is 460, plus the displacement of CGS from CGC at the critical location, which is given as Y. Thus, D is equal to 460 plus 20 is equal to 480 millimeters. That is, the depth of the CGS at the critical location is equal to 480 millimeters. From this, we calculate the percentage of the prestressing steel, which is 100 times the total area, which is 960, divided by the breadth of the web, which is 100, and the depth of the CGS, which is 480, which gives the value of 2. From table 6, for M35 concrete, we can find out tau c is equal to 0.86 Newton per millimeter square. The code gives the value of the tensile strength of concrete as corresponding to the amount of prestressing steel. What we had observed earlier, that as the prestressing steel increases, the tensile strength of the concrete increases. The variation among the grades of concrete is not too much from the value given in the code, and corresponding to the amount of prestressing to be 2%, we found out that tau c is equal to 0.86 Newton per millimeter square. Next, we are calculating the term m0, which is the moment that generates a flexural crack at the location of the design for shear. m0 is given as 0.8 times fpt times I by y, and as I said that this is equal to 80% of the moment that decompresses the CGS at the critical location that we are studying. FPT is the compressive stress in the concrete at the level of CGS, which is given as minus PE by A minus PE times Y, which is the eccentricity of the CGS with respect to CGC, times Y, which is the distance of the CGS from the CGC, divided by I. Thus, we are calculating the stress in the concrete at the level of the CGS at the critical location. PE is 826 kilonewtons, which is changed to 826 times 10 to the power 3 newtons. Area is 159,000 millimeters square, and Y is 20 millimeters, and I is 1.7808 times 10 to the power 10 millimeter to the power 4. And once we substitute the values, we find that FBT is equal to minus 5.21 Newton per millimeter square. Thus, the stress at the level of CGS due to the pre-stressing is given as 5.21 Newton per millimeter square. From this, we calculate the value of M0. M0 is equal to 0.8 times 5.21 times I, which is 1.7808 times 10 to the power 10, divided by Y, which is 20, which gives a value of 3711.2 kilonewton meters. We have to also calculate mu at the critical section. Mu at the critical section is given as 1.5 times Wt times x by 2 within bracket L minus x. Once we substitute the value of Wt, x and L, we get mu is equal to 47.6 kilonewton meters. We are substituting the values of the calculated variables, and we find VCR is equal to 1 minus 0.55 times 0.58 whole within bracket times 0.86 divided by 10 to the power 3 to change Newton to kilonewton times 100 times 876 plus 3711.2 times 233.3, which is the VU at the critical location, divided by 47.6, which is the moment at the critical location. And once we substitute, we find out that VCR is equal to 18256 kilonewtons. This is a substantially high value because the second term in VCR is substantially high. This means the shear corresponding to a moment that will generate a flexural crack at the critical section, which is at the face of the support, is extremely high. We do not expect to have a flexural crack near the face of the support, and hence in this particular situation, VC is the lower of VC0 and VCR, and we select VC is equal to 259.4 kilonewtons, which is the value of VC0. Thus, what we find is that at the face of the support, the VC0, which is the shear required to generate a web shear crack, is much lower than the shear required to generate a flexural crack and to change the flexural crack to flexure shear crack. Thus, near the support, the capacity of concrete is governed by the web shear cracking, and that is given as 259 kilonewtons. What we observe is that for this particular section, the demand, which is VU, given as 233 kilonewtons, is in fact less than VC. The fourth step is to calculate ASV divided by SV. Since VU is less than VC, we are providing minimum amount of stirrups, which is given by the expression ASV by BWSV is equal to 0.4 divided by 0.87 Fy. Next, we are calculating the maximum spacing. There are two expressions of maximum spacing when the VU is not substantially high. SV is equal to 75% of dt is equal to 0.75 times 876 is equal to 656 millimeters, or SV is equal to 4 times BW, which is equal to 4 times 100 equal to 400 millimeters. Out of this, we are selecting the lower one, and hence the maximum spacing is equal to 400 millimeters. We are selecting SV equal to 400 millimeters. The sixth step is to calculate the size and number of legs of the stirrups. Select Fy is equal to 250 Newton per millimeter square. ASV is equal to 100, which is BW, times SV, which is 400, times 0.4 divided by 0.87 times Fy, which is 250, gives me a value of ASV is equal to 73.6 millimeter square. Provide two-legged stirrups of diameter 8 millimeter. Thus, we are providing ASV, which is equal to 2 times 50.3 equal to 100.6 millimeter square. The required value was 73.6. We are providing 100.6 millimeter square. There is another provision of minimum amount of stirrups, and we are checking that in absence of dynamic loads, ASV mean is given as 0.1 AWH, where AWH is the horizontal section of the web for a distance of SV, which is given as 100, which is the breadth of the web, and the length that we are considering is SV, which is equal to 400. From this we get ASV minimum is equal to 40 millimeter square. Provided amount of stirrups, which is 100, is larger than ASV min, hence it is okay. Now in this case, the amount of stirrups that we are providing here, the support, is itself minimum. Hence, we are not changing the spacing of the stirrups along the length of the beam. We are providing same spacing of stirrups throughout the span. Next, we are designing the stirrups for each flange. First, we are calculating the area of half of the flange. A1 is equal to half of BF times DF is equal to half times 435 times 100 gives A1 is equal to 21750 millimeter square. The distance of the centroid of A1 from CGC is equal to 410 millimeters. The expression for the maximum stress in the flange is tau F max is equal to Vu times A1 times y bar divided by I times the breadth of the flange, which is the dF. This is equal to 233.3 times 10 to the power 3 to change kilonewtons to newtons times 21750, which is the value of A1, times 410, which is the value of y bar, divided by 1.7808 times 10 to the power 10, which is the value of I, times 100, which is the value of dF. Thus, tau F max is equal to 1.17 Newton per millimeter square. We are calculating the shear in the flange, which is equal to tau F max divided by 2 times BF divided by 2 times DF is equal to 1.17 divided by 2 times 435 divided by 2 times 100 is equal to 12724 newtons. The stirrups in the flanges is calculated as Vf divided by 0.87 Fy is equal to 12724 divided by 0.87 times 250 is equal to 59 millimeter square. For minimum still, ASVF is equal to the breadth of the flange in the direction of the shear flow, which is actually dF, times SV times 0.4 divided by 0.87 Fy, and when we substitute the values of dF, SV and Fy, we get ASVF is equal to 73.6 millimeter square. Thus, the minimum value is governing, and we can provide two-legged stirrups of 8 millimeter diameter in each flange. The design stirrups are shown in this sketch. We are providing the same amount of stirrup in the web and in the flanges. It is 8 millimeter diameter stirrups at the maximum spacing, which is 400 millimeter center to center. Note that for each of the stirrups, we have provided longitudinal bars at the bends, and the size of the longitudinal bars we have selected, which is greater than 8 millimeters, which is 12 millimeters. Thus, in today's lecture, we studied the design for shear. We first studied some general comments, how to calculate the shear demand. We can use the shear coefficients for continuous beams. For simple supported beams, we can use the beam theory. And then we moved on to the design steps, that we are selecting the critical location. First, we are calculating the VU, the shear demand at that critical location. Next, we are making sure that the average shear stress in the critical location is less than the maximum permissible value. This is to check shear compression failure. Once we have done that, we are calculating the shear capacity of the concrete, Vc. The shear capacity of concrete is given by two expressions, one for the uncracked section and another for the cracked section. The code recommends to evaluate both the expression at every location. Once we have evaluated the two expressions, we are picking up the smaller values of the two as the value for Vc. If Vu is less than Vc, then we should provide minimum amount of stirrups, and we have seen that expression for the minimum amount of stirrups. There is also an additional requirement of minimum amount of stirrups, which is in terms of the horizontal area of the web. If Vu is greater than Vc, then we have to design the stirrups, and that design is based on the amount of stress carried by the stirrups. We also learned about the design of stirrups for flanges. The flanges are subjected to shear due to the shear lag effect, and we saw the expressions for designing the stirrups in the flanges. We saw the design procedure through the help of an example, and with this we are ending the analysis and design for shear. In our next lecture, we shall move on to the analysis and design for torsion. Thank you.